Okay, welcome back, everybody. I hope you had a good lunch and a good chat to your colleagues. We're going to move on to our sort of middle session now around the works of fib and some of the outputs from those that feature in bulletins or bulletins underway. And we have two speakers in this session. So I'm delighted to introduce our first speaker. That's Mehdi Kashani. Mehdi is an associate professor of structural and earthquake engineering at the University of Southampton. His work focuses on the structural assessment, retrofit, resilience of existing reinforced concrete structures and bridges. He's got particular interest in deterioration, corrosion, dynamics response under earthquake loading. He's authored more than 130 publications, and he contributes to international guidance on modelling the performance of existing concrete structures, including practice aligned with FIB Bulletin 111. And that's great because Mehdi is going to be presenting to you today on structural assessment of existing RC structures and bridges, FIB Bulletin 111 and beyond. So Mehdi, the floor is yours. Welcome.
Thank you very much, Chris. Nice introduction. I'm going to talk about a bit today. 1/3 of my presentation is about this Bulletin 111, and the remaining is a new working group that we established within the Commission 1 of the FIB, as well as some of the underlying research. And I bring you a couple of examples that will feed into the future bulletins. So just to give you an introduction, this the outcome of this Bulletin 111 is part of the group task group 3.2, part of the Commission 3 of the FIB, which is on the existing concrete structures. So the table of contents, I'll just give you a brief overview of what's in there and some flavor, just some of the key outcome of this bulletin. So the first, essentially, chapter of this bulletin is essentially developing terminologies and some fundamental concepts. But the main are 5, 6, and 7 on the material bond, and the 7 is essentially a series of different performance levels that we can do. I'll just give you a few examples. This was the first attempt of this task group on the existing structures, but then there are some following up research that we currently undertaking. The scope of this bulletin is essentially, does this work? Well, not that. So this is essentially the graph on the left that you see is the typical life cycle graph that you see in any kind of concrete or any kind of structures. That's essentially the performance of the structures over the time is degrading, and we need to provide a preventative maintenance to be able to bring the performance into an acceptable level. And also on the other graph on the right side, it tells us that as we increase, the performance is reducing, the loading of the structure is increasing. So this loading could be due to traffic, train, or nowadays we have more kind of aggressive environment like excessive rain, hurricane, storms, etc. So when we were writing this bulletin, the Model Code 2020 was not out yet. So it's mainly based on the 2010, Model Code 2010. But also 2020 is the same philosophy. The only difference is that 2020 has more on the existing structure that is aligned. And the future bulletin that we are working on will be aligned with the Model Code 2020. Moving on to the next chapter on the material. So there are a lot of problems with either concrete or reinforcement. So if you look Northern Europe, Scandinavian countries, or north of France, Switzerland, that they have got mountains and snow. So a lot of the problems that they have is the frost-induced crack and degradation of the concrete. We don't really get that much of that in the UK, although we got some cold weather, but it's not extensive like what we get in the extreme weather. So there are some models that some of the research that have been done by our European colleagues, so they included in this bulletin. And there are equations. I didn't put any of the equations. I just showed you example of the graph. So you can see the comparison between the undamaged concrete and the damaged concrete, that how you can get the reduction in the the strength of the concrete and also the decay, that's how it's developed. And then these are some recommendations if someone wants to include in the numerical model, or they want to use them as sort of for the simplified calculations. We also lightly touch on the impact of corrosion on the bars. So this is very brief in this bulletin. So when they were writing this, the new DMRB had not come out yet. So this is based on some of the assumptions that they wrote is based on the old DMRB code, the BA standard, 1993. But the new DMRB also essentially implementing the same idea. And this is another model by Vald et al. That is essentially considering how we can account for the pitting corrosion. So if we can measure the corrosion on site, if the rebars are essentially exposed, so we can use one of these models. The equations are available in the bulletin to account for the residual diameter, residual cross-section area of the corroded bars. But that's not the only effect that corrosion has. But also corrosion, what it does, it actually changes the behavior of the material. It doesn't change the behavior of the parent material, but the reason it is changing is because when you have got, for a given length, you have got non-uniform pitting. So wherever is the minimum cross-section area starts under the tensile force, start yielding, and then the other one start yielding. So this effect is essentially changing the behavior, and you can get localized yielding. So essentially the ductility is reducing, and also the air and also the strength. The strength, the reason it's changing because we cannot, whatever we do, we cannot calculate the exact area. So that's why we sort of tweak the yield strength with like a coefficient, we call it pitting coefficient. So we reduce the area and then we add the pitting coefficient to account for this. So some of these recommendations are in this existing bulletin, and there are more detail coming up in the future bulletin. Moving on, bond slip behavior is a big challenge. So this is another, this is an example of the graph that our colleagues in Chalmers, they did a lot of work on corroded bond behavior, impact of corrosion on bond slip behavior of bars, essentially bare bars, plain bars, or with bars with the ribs, with and without confinement. They did a lot of different tests. So the simplified version that is brought to this bulletin is essentially when you have got the original bond slip based on the model code 2010. So essentially they shift it back and they reduce the maximum bond strength. So to modify this. This model is actually included in the Diana software if you want to use any of these softwares for bond strength behavior. So you can use it, or you can simply code it as well. So it's not that complicated to be able to use it in the calculation. Also, there's some comparison between the maximum bond strength based on the model and based on the model code. So this is the analytical model developed, and this is the actual model available in the model code. And there are more details coming up. So in the new bulletin, I will discuss it, that we are working, we do more on the corrosion. So this particular bulletin did lightly touch on corrosion, but there are more coming up because of the corrosion. Moving on, the next chapter is a range of parameters on flexure, on the detailing, on the shear, but I bring some example on the shear. So essentially it provides recommendation on the beams and columns and slabs, how we can assess them in the shear. So these are some of the classic some of the classic shear failure in the plain concrete, and also the shear interlock concept. And there are some equations that you can use it. So essentially, some of this work in the bulletin is I think fit to the model code 2020, which ultimately went to Eurocode 2 second generation as well. Also, some of the other one on the punching failure, whether it's a slab, like when you get this essentially membrane action, or the punching failure of the slab. And as I said, these are the colleagues in EPFL. They did a lot of work on the punching shear behavior of the concrete. So there's a lot more in the bulletin if you look, and as well as the flexure behavior. So it's quite interesting. And what hasn't been done yet on these things is, if you have got deteriorated structure, what would happen? So that's an open question that we need to do more research on this. And finally, before we wrap up the finishing of this bulletin, we largely touched on the capacity of the deteriorated structures, and we discussed a little bit on corrosion. So if you go back, there is a bulletin called Service Life Design of Concrete Structure back in 2006 that is discussing some of the analytical method to calculate the corrosion initiation and corrosion propagation at that time. So that has been some of it reflected here, but also there are a lot of new work happening in the other commissions of the FIB, but also within this group, we have got other people that in the new bulletin that we are working, we will discuss it. But in this bulletin, essentially we discuss two fundamental mechanisms of the corrosion. It's either carbonation-induced corrosion or chloride-induced corrosion. So carbonation-induced corrosion is essentially the concrete cover. It reacts with the CO2 in the air. So in the UK, we don't have that much problem with the CO2 or with the carbonation. So what we have with the problem in the UK is mainly chloride-induced corrosion. So it's mainly because on the day like today, it's freezing cold and we got frost on the road and we put salt. And that salt is melting and then is essentially penetrating through the concrete cover, and concrete is essentially like a sponge. It has porosity, and this is sucked into the concrete, and then when you get to that certain level, they call it chloride threshold level, which is normally 0.4% of the cement, that is changing the passivity between the interface of the concrete and the sleeve, and that reacts and starts the electrochemical process of the corrosion. And what would happen is, you have got an initiation period. So there are different methodologies. The most famous one is Fick's second law of diffusion. But chloride has diffusion and convection. So essentially it's a partial differential equation to solve it. There are some solutions for this equation to solve. And then you can get sort of the time, probabilistically, the corrosion initiation. So that's not where the damage starts. When corrosion starts, they start propagating if we do nothing. And we cannot normally see it unless we do NDT, non-destructive testing. And then when corrosion develop, it start having some cracks, and then eventually it's falling off the concrete. But the thing is, between the corrosion initiation, and to the spalling, we have lost some reinforcement. We don't know the residual capacity, so that we need to have this ongoing sort of measurement through the inspection to be able to have understanding our structure. So spalling is essentially too late by the time we get to that stage. That's a little bit of it is discussed in this bulletin, but we will be discussing this in the future bulletin. So the future bulletin that we're currently working on is essentially the provisional title is Models for Bearing Capacity of Concrete Structures with Corrosion Reinforcement. I don't quite agree with the bearing capacity. I would call it residual capacity, but our European colleagues, they like to call it bearing capacity. But anyway, it's a residual capacity of the concrete structure because of due to corrosion. So we will start essentially at the moment. There are people working on this model to predict and to provide guidance how we can predict based on the site measurement data, corrosion initiation and propagation, and then how this material properties, reinforcing bar under monotonic and cyclic loading, or it's buckling when you have got seismic loading. So I will touch on that a little bit after this today on some of the models and their underlying research that will feed into this. And the bond behavior, a bit more detail on corroded. And then when it comes to member, flexure, shear, axial shear, flexure interaction, and how we can essentially use them in the modeling, simplified modeling versus detailed modeling. And then we have got a lot of connection, detailing beams, columns, anchorages, half joints. So this is quite a big problem in Italy. So I have a lot of Italian colleagues working with us in these particular bonds. So there were a couple of bridge collapses in Italy. So that's quite critical. And then finally, we will do some sort of case studies. So and to bring these examples. So it needs another couple of years for this bulletin to come out. But along the way, when we were working on this, so I had a chat with the chair of the Commission 1, that in the Commission 3 is existing structures and task group 3.2. We do a lot of work on the component level, and there are some people discussing bridges or rebuilding, but I felt that there is some specific group missing to discuss problems related to bridges. Because bridges, we have problem with the deterioration, but also the loading and some other problems. So we decided to establish a new group, a working party that just came out, established this year, So I'm chairing that working party. Chris is part of one of the members in that party. So essentially what we discussed, we said we have an awful lot of bridges in Europe and internationally that they are deteriorating. The loading is increasing. We will have a lot of extreme weather conditions coming up. We have problem with the sustainability. And with bridges, it's not just a problem with the material. So when we want to shut down bridges to do any intervention, the indirect cost, CO2 and cost, is quite large, is huge for the bridges compared to like buildings. So we wanted to have these objectives for this to discuss to work on model specifically for bridges and how we can extend the service level extension methodology specifically for bridges that are tailored for bridges. And we are hoping to discuss and to have a bulletin by 28, roughly 27, 28. It's a bit quite ambitious, but we are working on that group. So at the end, I will put my email. So anyone who's interested to be involved, to get in continue to for either this group or task group 3.2, please do get in touch with me. Now, so I'll give you two examples of the underlying research that will feed into the new working group party, the group, and also the task group 3.2 for the corroded structures bulletin. So this is an example of the bridge pier test that we did in Southampton. There were 6 bridge piers. 4 of them were carbon steel, 2 of them were stainless steel. So the details are in these 2 papers underneath that are presented. You can see all the details. I'm just presenting some outline of the results. So the stainless steel one were seismically designed according to Eurocode 8. I'm not discussing it today. I'm focusing on the corroded one. The corroded one had some of them. We will see this is well confined, designed according to Eurocode 8. This is lightly confined, essentially representing all the columns. And then we had for each group, essentially corroded and uncorroded. So this is how we corrode them in the lab. This is the backyard in Southampton. So we have got the columns. We create a bathtub. So if we put a stainless steel column, a stainless steel plate, they act as a cathode. And then when we were building the columns within the building, so we designed it, we gave them an external contractor. So essentially the columns were bars when they go into foundation. So we had cables coming out, connecting to the vertical bars, and then we attached them to the power supply and we corrode them. And we add salt water. So we call it anodic corrosion, which is essentially a reverse of cathodic protection. So, and we accelerate it. And how we accelerate it and the rates, we have to be realistic, because if we accelerate it too much, it will explode the cover too quickly, and it's not realistic. If we do it very slowly, it takes too long. So based on the experience that we had, we found the number that normally the measure is, they call it corrosion current density. So roughly around 200 milliamp per centimeter squared surface area of reinforcement, what we get, the rough number. There are some papers that have done some parametric study, and we tested over the past 15 years I've been doing this, that's about right. And after the corrosion, you will get something like this. So you see the vertical bars and the corroded products coming out. This is the test setup. So the bridge pier under cyclic loading, because when you have got earthquake, so the bridges, when you have got multiple span or a single bridge pier, so the earthquake is 2 components. The perpendicular component, essentially the bridge piers are behaving like a vertical cantilever beam. It's a predominantly flexural behavior. And this is essentially, we put some DIC spackle here to measure the moment curvature, and we have got LVDTs to measure the horizontal deformation. I also added a couple of accelerometers. I did some hammer tests, which I'm not presenting here, to get some dynamic properties that is essentially degrading, that potentially can be used for health monitoring. That's out of the scope for today, but it's available in the papers. And this is the result. So after we test the reinforcement, the columns, so we demolish and we take the reinforcement out. So if I refer back to this figure, this section A, B, C, essentially 200 millimeter and 200, 200, 200, essentially 3 segments, each of the 200 millimeter, we demolish and measure the mass loss of every individual bars. So there were 9 bars across the section and the hoops. So this is essentially like a heat map of the mass loss percentage of the corrosion. And this is a global response. So this is the uncorroded, well-confined design according to Eurocode 8, but you will see you still get some buckling on the cyclic load, and you see this fracture. So this fracture is known as low cycle fatigue behavior. So in earthquake, unlike the normal structure that we have got, low amplitude, which is the amplitude of the loading is low, high cycle, which gets millions of cycles. In earthquake, is high amplitude, low cycle fatigue. That means the amplitude of the loading is high. With like a few cycles, we get fractured because of the plasticity. And when we got buckling, we get double effect. Because of the buckling, we get stress localization, and the bars fracture even quicker. And this one is the well-confined column after the corrosion, which essentially had minor buckling and mainly governed by the flexure failure. And this is the lightly confined concrete, and you see is governed by the compression failure. And we can see it in the response. So this is essentially the two fracture bar after the low cycle fatigue. And this is essentially when the bars started fracturing in tension. And these are essentially fractured, but this degradation comes from, a lot of it is from the concrete crushing. So it's a different failure modes. This is also showing in the DIC pictures. So this is an example for the column A, uncorroded. You see just classic flexure cracks, essentially horizontal, to the perpendicular to the direction of the loading. But when you have got corrosion, we start getting this weird vertical crack, which is essentially because of the corrosion of the vertical bars. So even before we start getting the loading, you get some vertical crack. But as we load the structure, we get tensor, these cracks start opening up. So it changes the crack pattern. So this was the experiment, but the most important part is this bit, to be able to model this. So these experiments are benchmark experimental tests that we normally do, but we want to model them. So a lot of material model that we have tested over the past few years, and we use them in the fiber-based model. So these are essentially nonlinear beam column elements that we have got. In each element, we have got different integration port, and each integration port we have cross section. And based on moment curvature response of the cross section, we can integrate across the element to get material nonlinearity. So, and there are methods, this is called distributed plasticity, and there are methods called lump plasticity. Essentially, we can assume a plastic hinge and just have another beam with elastic. In earthquake engineering community, it's very common because it's quite fast, computation very cheap relatively compared to like Abacus or any other software. And we can run thousands of simulations. We can do fairly detailed. So the only downturn or the only problem is the accuracy of the model is purely dependent on the uniaxial material model that we use in the model. So essentially for steel, for concrete, for confined concrete, if we include buckling, etc. So we did that. So if you want to interest more detail of this, I can provide you the papers because there could be another whole presentation on this topic. But then we did the simulation, and this is the result of the test. So we could simulate, this is the backbone curve. Essentially, we do pushover. Pushover is just monotonic push to get the capacity, and then also the cyclic. And we could simulate the fatigue and the failure of the column. And we could see this is essentially when bars buckles, essentially when you have a buckling of the vertical bar, they lose the strength and increase the stress in the concrete, and concrete crushes quicker. And that what we see in the degradation of the column response. And it is on the cyclic loading, we have got combined tension with the compression. But this kind of model is quite useful, and I'll show you in the next few slides that we can use it for the UK problems as well. And then we looked at it. So we had essentially 27 different material models at all these three sections. And I said, when you have a non-uniform corrosion, we start rotating the bars around the section. So this is 9 bars. Imagine we rotate them. You see, this is stress state of the bars at the final stage. And you get this response. So it's quite important to be able to identify this localized corrosion, how it behaves. So otherwise, depends on the loading direction, we get a different capacity. So that's another thing that localized corrosion is very important. And this is also some examples of the material response. So this is the confined concrete response in column A1, which was well confined. This is column B1, which is lightly confined. You see, essentially, the concrete crushing strain is around 0.4%, which is more or less like unconfined concrete. But whereas this one is much more, so we had better confinement. So this is, and this is with the buckling, and this is where we have got the buckling without the buckling and the fatigue damage. So we could include cumulative fatigue we could see. So essentially the power of the OpenSys is we can track every single material. We can track, we can see, we can eliminate, we can understand how things are failing at different level. Moving on, another project that actually my PhD student is here, so she's done all this test, is for assessment of the corrosion damage bridge decks. So all of us, we have got a lot of bridge engineers here, so we use grill edge quite often in analysis of the bridge deck, but the grill edge is based on elastic analysis. In network rail, for example, for the level 2 assessment, for metallic bridges, they do a lot of nonlinear. But for concrete bridges, we cannot do it because of the complexity of the 3D modeling of the concrete. But with the fiber model that I've shown you for the earthquake, which is quite common, we can use it. We can essentially develop a nonlinear grillage model that can capture the distribution of the plasticity within the bridge slab. But we need to have some tests, uncorroded essentially slab, to be able to develop models, combined with some high fidelity finite element to generate more data, to be able to calibrate the grillage model, and then eventually we can put it in a whole bridge that we have got the pier with the deck and everything else. So we had 6 slabs, single layer, double layer, a bit different. These are estimated corrosion. We will measure the corrosion afterwards. Same methodology, accelerated corrosion. And this is the test arrangement. So it's a two-way slab, simply supported. We didn't want to deal with the boundary condition. Essentially, it's a simply supported all around that can give uplift. And we got a 500 kilometer actuator in the middle. So I got 2 optical fiber. These are high resolution optical fiber that is there. And then afterwards, we could essentially measure the corrosion. We get essentially the map of the corroded slab. And this shows that the failure mechanism is essentially changing from punching to flexure failure. And we can see the crack pattern. So you see single layer is a punching failure, comes to a flexure, punching flexure, and then finally comes to a flexure as corrosion is increasing. The double layer is similar. So we get a bit of punching, and then it's a punching flexure, and then it goes towards fully flexure behavior, and the deformations are quite unsymmetrical. And again, this is the crack pattern. So the fiber optic also shows that we can detect it under the top and bottom, and this was the static. And these fiber optics, they are able to get the dynamic measurement. So they have the bandwidth of these optical fibers are 500 kilohertz. So we can essentially, any small crack, we can detect it. And this is essentially a hammer test. We did the time history of the data, and then we did the FFT, and we could actually see the frequency change, which is essentially related to stiffness, and can be used for health monitoring in the future. So coming up, we will use some of these results along with some, we are planning to do some pre-stress beams, as well as some smooth bar columns to test for the, against on the cyclic loading to be feed into both these bulletins. Hopefully in the future, next year or year after, I can present you a bit more updated results. And finally, I would like to thank for my PhD student. One of them is here, and the others who are not here, and also our funders, UKRI, EPSRC, European Commission, Network Rail, RSSB, and the UK Lab in Southampton. Thanks very much for your attention.
So our next speaker is José Manuel Sena Cruz. José is an associate professor at the University of Minho in Portugal. He's also co-director of the Institute for Sustainability and Innovation in Structural Engineering and director of the European Masters in Advanced Structural Analysis and Design using composite materials. His work has been strongly focused on composite materials, covering research, training, design and consultancy, and he's been heavily involved in work for both FIB and several committees, and also in the European Eurocode committees as well. So José will be presenting an overview of externally surface bonded and near surface mounted strengthening techniques with CFRP composites. So thank you very much.
Thank you for this introduction. Good afternoon, all of you. So I'm going to talk about basically this FIB bulletin, this 103, and mostly devoted to chapter 7. And then using this, I'm also going to show you some contributions that we are doing in the scope of the topics related to this bulletin. So starting with this bulletin 103, so it's in reality, it's not so scientific as you have seen in the previous one. So it was developed by this task group 8.1 from Commission 8. It was released in 2022. It has more than 300 pages and 12 chapters. So you can see here that in reality, this bulletin is devoted for those that are not familiar with different strengthening techniques for different types of structural elements that we have in concrete structures. So you can see here different types of solutions. Where is the point is? different types of solutions, and I'm going to give more detail about chapter number 7, which is related to external applied or near surface mounted FRP. So this chapter follows the structure that we can see in the other chapters of this bulletin. It's composed of different parts, includes the basics, design, stakeholder roles, qualifications, execution, quality control, monitoring, maintenance, and also in all of the chapters you could see 2 case studies to somehow to give you more details about this. So as I mentioned before, this is a relatively basic information for those that are not familiar or wants to be aware how to apply these techniques in real cases. Here you can see the list of the authors of this chapter. So basically in my presentation, I'll not give focus to all the components, but some of the parts. So I'll start with the basics. So then I'll move and give you some information about design, about execution, quality control also. And then I'll give you a small summary about these 2 case studies that are included in this chapter. So starting with the basics. So basically, somehow we already discussed this in the morning. So composites from material point of view, they are heterogeneous materials, anisotropic, and in general, they have linear elastic behavior until the failure. So this creates more complexity compared to our traditional materials like concrete or steel that we are more familiar. So basically here you can see a microscope view of a composite, a carbon composite. It is composed of fibers, that is the dispersed phase, but in reality is in charge of stiffness and strength of the composite. And then you'll have the matrix, which is in charge of protecting the fibers and shear and the stress transfer between the fibers. It is the continuous phases. The typical fibers that you use in structural engineering are carbon, glass, aramid, and basalt, while in the case of the matrices, normally you use epoxy, unsaturated polyesters, or vinyl esters. The typical FRP systems that we use for structural strengthening of concrete structures are the ones that you can see here, precure systems that already includes the matrix and the fibers, while in some cases you use these wet layer systems that we have seen, for instance, this morning for shear strengthening, where we apply these FRP sheets with an adhesive that at the end creates the composite. In some special applications or in some special uses, we have special systems that are convenient or sometimes they are required. Here you can see some examples from the market. So for instance, these ones here are normally used when we use pre-stressed FRP systems. Here, for instance, for improving the shear capacity or even avoiding as much as possible debonding at the end. And for instance, these spiked anchors that also are used to improve the bond or avoiding the delamination as much as possible. In terms of the strengthening techniques, so from several ones that have been proposed over the years, there are 2 main that prevail. So basically, one of the most used one is this EBR. EBR stands for externally bond reinforcement. Is mostly used for flexural shear and confinement. And basically, as you can see here, we have to apply the composite on the tensile zone of the element to be strength with an epoxy or a bonding agent. The other technique is the near surface mounted. Is mostly used for flexural or shear strengthening. And you can see here in this case, what we have to do is to insert the composite material in the concrete cover of the element to be strengthened. Here are typical failure modes that we have already seen in this morning, so I will not spend too much time with this, but in reality, when we compare this near surface mounted technique with EBR, you can see that this NSM presents more advantage like reduction of the amount of site installation work, less prone to premature debonding, less visual impact, as you can see here, higher protection of the system against external environments, and in many cases you can achieve the ultimate capacity of the material, in addition to the fact that be possible to anchor at extremities. When we go for designing these systems, we have to always answer to 3 questions. I'm going to give you two of these questions that we need. One is, should we use a passive or active technique? What is a passive technique? Is one technique where when we apply the strengthening system, this strengthening system will start only sharing stresses if we apply extra loads. Otherwise, this system doesn't work. In some cases, we need to have active systems like pre-stressing. And this one, the system, the reinforcing system, starts sharing the loads since the beginning. Another important thing is always we have to select what kind of strengthening system are you going to use, if it's a selective or a total. Here is two examples of selective techniques. For instance, this one is near surface for improving the flexural capacity. This one here is for improving the confinement. In some cases, we need all, and typically call this total strengthening. Okay, now moving to design. Basically, somehow this morning we already discussed this. So prior any design, we have to do an assessment of the existing structure to verify the state of the structure. Yeah, and this is the first stage. So basically here I put some examples that also are referred in the bulletin, about codes and the guidelines that exist. And particularly this one here that is from the second generation of Eurocode 2, where we have this Annex A and I that somehow already include information how to assess the condition of the structure. Since these techniques are nowadays a state-of-the-art, you can find out also codes and guidelines available for designing the solutions, okay? So again, here, I would like to also refer the second generation of Eurocode to the Annex J that includes the strengthening of existing concrete structures with carbon systems only for different types of situations like shear, flexural, and confinement. But in any case, you can find out other codes that can assist you in the design of this solution. Most of us, for sure, are structural designers, and you are familiar with a series of principles and assumptions that we do during design. And when we use or when we design solutions with composite materials, we'll exactly follow the same ones, but then there are some ones that are new. One is clearly this one here that I would like to say is we have to always to assess the initial stress state of the structure, because this is essential for proper design of the structure. Another one is typically these type of solutions cannot be assumed that they carry compressive stresses. So only tensile zones can be applied. And finally, these two last ones is typically you need to use constitutive laws to assess load carrying capacity of the concrete. And for that, you use the existing codes. But then for the case of FRP, it becomes simple because we can assume that material behave linear elastic until the failure. So this is for ultimate limit states. For serviceability limit states, the approach is very similar. And here again, I would like to highlight these two. We cannot use this material for carrying compressive stresses. We have always to access the initial stress state because it's fundamental for a proper design. And then for all the materials, now we are going to assume linear elastic behavior because this is serviceability limit conditions. Tension stiffness is always very important, and now the complexity is higher because in addition to reinforcement, we have to consider the FRP in this global assessment of deflections. Okay, so typically you have to follow the procedures regardless of the code that you are going to use for flexural or shear strengthening. So the first stage is always to verify the original condition of the structure, and typically you are going to conclude that we need to improve the load carrying capacity. Once we do that, then we have to verify, do a verification about the accidental loss of the composite. Normally this is done with using accidental combination of actions. And once verified, then we have to assess the initial stress state of the element to be strengthened. Then at the critical cross-section, we define the needs in terms of the composite, and then there is an iteration procedure in order to verify all the requirements at ultimate and serviceability limit states in order to design the solution. Once defined, when we talk about flexural centering, we have always to verify the shear capacity, because in many cases we increase the flexural capacity that creates fragility at shear level, and this is necessary now to design supplement shear capacity. So basically, the idea here is to verify the need of shear capacity given by the composite solution. Then we have to start defining configuration. Again, this morning we have seen, for instance, this U-jacket that is probably not the most efficient way. Probably the most efficient way should be, for instance, fully wrapped, but is more complex to do. And once we define the configuration, then we can design. And again, all these codes already provide you provisions to design the solution. Okay. Talking about execution, so this is also a part of the document, of the bulletin. So there are always preparatory works to be done. Basically, somehow we already addressed this afternoon of this. So we have to remove all the degraded and contaminated concrete. Okay, so this is mandatory. Otherwise, corrosion will come later. So we have to avoid this. In many cases, we have to repair, clean, protect, and sometimes add bars to replace the corroded ones. Typically, there is a suggestion every time that we face more than 10% of reduction of the cross-section, we should replace with a new bar. And then in many cases, we have to add concrete sections using mortar, microconcrete, or concrete, depending on the level of needs in terms of volume. Finally, typically we have also in the existing structures cracks, concrete cracks, and if the cracks are wider than 0.5 millimeters, it is always suggested to seal or inject these cracks prior the application of the system. Here you can see the different steps that we have to perform in order to apply the external bond reinforcement with pre-cure FRP systems. So we start identify the zones to be strength, then the surface should be prepared and check if there is out of plane variations that I include here, but in the bulletin you have this information in order to avoid premature debonding failure modes if you don't follow these rules. Then we have to clean the surface, also clean the reinforcing material, prepare the adhesive according to the supplier instructions, apply the adhesive on the surface of the element. And since these materials are really light, you can see that can be easily handled by hand without any lift to apply it. Then, of course, you have to press in order to have the adhesive flow to the lateral faces, clean the laminates, and finally, after curing, you have to check if there are eventual voids, and if needed, you can also add additional protections. In the case of external bond reinforcement with wet layup systems, the procedure is relatively similar, but in the case, for instance, of applying for the shear strengthening, we have to round the edges. Okay, so again, here, if you go to the codes, you'll see the minimum radius that is recommended for this. Otherwise, we'll have the failure here at these corners. Okay, so then again, you have to verify out of plane variations, clean the sections, cut the FRP sheets according to the design details, prepare the adhesive, apply the adhesive on the surface to be strength, saturated also the FRP sheets, and then apply the FRP sheets, removing the excess of adhesive. If we need to apply more than one layer, then we have to repeat again this process until comply all the requirements detailed in the design drawings. And then here you can see an example how it looks at the end. Finally, in the case of near surface pre-cure systems, so basically the first step is identify the zones where we are going to apply the composite material. So then open the grooves or execute the grooves, typically use socket machines. Here it helps because the gravity is helping. When we have to do, for instance, for positive bending moments, it's more challenging, but it is feasible. Okay. Then we have also to cut and clean the composites, prepare again the adhesive, applied inside the grooves the adhesive, and then we install the CFRP system. Okay, so in some cases of structural application, somehow this is also a discussion during the morning, the use of pre-stress external bond reinforcements is convenient or might be required. So here it's a test of the beam, the longest beam that I test in lab, 20 meters long. And here you can see the benefits of pre-stressing. So this is the beam without any reinforcement. This is the beam with the passive solution. And here is the beam with the pre-stress laminates. So at the end, these are the main advantages when we use pre-stressing systems. So deflection, reduction, and acting against dead loads, crack width reduction, higher fatigue failure resistance, delay in the yielding of tensile reinforcement, reduce premature debonding failure, and increase the ultimate load bearing capacity and shear. The typical systems or examples of commercial systems that you can see in the market are these two ones that I'm going to detail, these mechanical anchorage and gradient anchorage systems. So basically how they work. So again, it's for the case of mechanical anchorage system, we have to start doing the surface preparation. Is always crucial, this. Then you have to install permanent temporary bolts. You apply the adhesive on the laminate, then install the laminate and fixed in the clamping system. Install the anchorage, metallic anchorage at the end. This frame is applied to accommodate the cylinder, and then you apply the pre-stress using the cylinder. This system is concluded 24 hours after the application because we have a certain level of curing of the epoxy. There is another one technique that is called gradient anchorage. So up to this step is exactly the same, but now instead of having metallic anchorage, we are going to use this gradient anchorage. How it works? So basically we have to have this heating device that I'm going to explain later on how it works. But basically you have to install, and then what we do is pre-stress the application and sector-wise heating the epoxy, following by a stepwise releasing of pre-stress. So this technique allows us to have all the process conclude 3 hours after the beginning of the application. Finally, this is a single slide, but is very relevant because it's quality control along all the process. We have to have quality control, otherwise these techniques will not succeed. So we have to have quality control in terms of material before, during, and after the applications. It's essential. Here I put only some parts that are in the document about, for instance, about the systems. We have to use or should use certified systems that the supplier must inform us about physical and mechanical properties, including critical ones for composites. Glass transition temperature information is fundamental for the success of the system, okay? Then before application, I would say that concrete is a key point. During the application, the environmental conditions are also essential. And after, we have to do also quality control of the execution. You can use non-destructive testing or minor destructive testing in order to assess the quality of the application. Finally, in terms of these two case studies, so the bulletin also, or this chapter also includes 2 case studies. One first case study, it was in Portugal. Actually, this is O Porto Airport, the runway, and there is this tunnel exactly in the runway. And at certain point, they realized in order to extend the service life of this tunnel, it was necessary to improve it to strength. So in reality, the solution was using EBR carbon laminates to improve the load carrying capacity of this tunnel. In the bulletin, we have all the details about how it was the process of designing and execution. A second case study was from a real case also in Poland. This is a bridge in Poland, and in reality, it was pre-stressed using this gradient anchorage system in order to improve the load carrying capacity of the bridge. So these two examples, you can find out all the details, how it was designed and how it was implemented. Now moving to the second part about contributions in these related topics that we have seen in this bulletin. So basically in our group about composites, we are addressing different types of things in terms of existing and new structures, of course, supporting in experimental, numerical and analytical tools. We do also a lot of inspection and diagnosis, quality control, and also standardization. So basically, we're involved in this new Eurocode 11 about composites, and also this Annex J about the Eurocode 2. Related to exactly the things that we have seen at the beginning. So let me So this is a short video, by the way, given by shared by S&P Clever Reinforcement, where you can see some steps of pre-stressing CFRP laminates with this mechanical anchorage system. So what you can see, it was the application of the laminate, fixing at the clamping machines, then installing the frame, and then here with the cylinder for pre-stressing the laminate. So at the end, you can see that, of course, then you have to remove all this excess of adhesive. Of course, this is designed for a certain strain level, and this is how it looks at the end. Regarding to the other system that you have seen, so basically this gradient anchorage is a non-metallic anchorage system that is based on the epoxy ability of cool faster at higher temperatures. So what we do is a gradual releasing of pre-stressed sector over several sectors at strip end. So here you can see some preparations of the test that we carry out in Minho, including measured temperatures because we have to apply temperature. And here you can see some results about the solution that we have used with 3 sectors. So basically, this is the temperature that we impose, the program of temperature that we imposed in the heating device. And this is the temperature that it is observed at epoxy adhesive in the first sector. Here is the second one, third one. In this graph here, what you can see is over the time, the strain that we have observed at mid-span and also the force in the jack for the different releases. And you can see that it was almost without losses except in the first sector. This is always common. And due to that, this was one of the things that we developed with this system. This was to estimate short-term losses of these pre-stress systems, because, you know, when we move to pre-stress, we have to evaluate short and long-term losses. In terms of short-term losses for this mechanical one, we have this. Unfortunately, I don't have time to explain, but this is when we fix the hydraulic jack, and the loss is around 3.5% of the strain variation. And while in the case of the gradient anchorage, you can see here we have always the same loss, but here is in the first release of the force, and is around 2.5%. Then we move also to some testing to compare the performance of both systems, and you can see here that both systems perform relatively well and similar until the failure by debonding of the gradient anchorage, because it doesn't have these anchorages. While in this one we have we can avoid this premature debonding due to this metallic anchorage. So this is the reason that we have a little bit higher capacity and of course much more ductility. We always nowadays, regardless of lab, DIC, and here I put it to prove that in this specific case the debonding comes from the middle part to the end. Typically we call intermediate debonding, which is another type of failure mode that we observe in this type of solutions. Of course, we also did numerical modeling to try to, for instance, to understand if the existing models, or if the existing knowledge is enough to simulate these pre-stressing systems. And you can see here the basically the continuous lines are the experimental curves. The dashed lines are the numerical ones, and you can predict pretty well the response, meaning that using relatively basic constitutive models, nonlinear models, of course, we can catch very well the response, including in terms of strengths, and you can see here for different levels. Another interesting thing that the system that I was involved with colleagues, mainly Professor Jacob Smith from DTU, was this activated ductile mechanism. So basically, it's a hybrid system where we have the CFR P bar, and at the end we install a spring. And this spring can be tailored in order to have a different response. So imagine this is the response typically that we have for carbon rebars. Then if we design properly this system, then we have a new response, which is ductile. And now we can have composite materials with ductile behavior, which is the ones that we have observed here with this is full-scale beams, and you can see that we could have a very ductile response of the beams, even pre-stress, but now with this ductile activated mechanism. To finalize, I'd like to also to show that we are also studying not short-term, but long-term, and durability and long-term is an issue. And what we have done was creating these several experimental stations indoor in our lab and outdoor in different places of Portugal, including we have also snow in Portugal a few times per year, not too much. But in reality, the idea here is to compare the accelerating aging test that we do at lab with natural aging, okay? We do this at material, bond, and full-scale level. And here, I only to show a few results in terms of material level, bond scale. And here, what was one of the most important things that we would like to provide was conversion factors that are needed to consider durability of these systems over the time. By the way, it is curious that the new Eurocode proposed the value of 0.7, which is in line with what we observe with the EBR, but for the case of near surface is conservative because our value was 0.85. Finally, to show you also a structural level, because we have seen these slabs that are loaded for more than 6 years. So these are results of displacements over the 6 years. These values here indicate the comparison with the displacement at short term or instantaneous deflection. But the most important one was we are trying to predict what will happen in 50 years for these non-pre-stress EBR and NSM, as well as pre-stress systems, because this is important while we design. And here, using some analytical models, for instance, based in this case of the generalized Kelvin model, we are proposing some factors, kind of, I could say, almost is not exactly creep factors, but close, that give you a possible prediction about this. Okay, so here I have all the literature that supported this presentation. And before leaving, I'd like only to give you a small advertisement. So basically, one is about this master that we also are coordinating about design and analysis of structures with composite materials. We have called for the next academic year. So, and it is a Erasmus Mundus with grants. And I also would like to invite you to attend the 7th FIB conference in Lisbon next year. The abstract submission is still possible. Just talk with me, because then I'll try to figure out how to solve the problem. So with this, I conclude my presentation. Thank you very much.